Hi everybody. Welcome back to Calculus and the chain rule, and believe it or not, we're not quite done with the chain rule. There's still one more thing that we have to do, and we have to talk about a different form of notation in the chain rule. And we're going to call this the Leibniz form of the chain rule. Let's start out by saying that y is a function of x, y equals f of x. Remember from not too long ago, maybe a week ago, that one way of denoting the derivative is f prime of x. Another way of denoting the derivative is y prime of x. And then we have this way of notating the derivative, dy dx. These two things, these two symbols, mean exactly the same thing. Now, the form of the chain rule that we've been using so far uses this style of notation. And that form of the chain rule is a good form. It's great for computation. Now, we can formulate the chain rule using this style of notation, and probably we should. We have two types of notation, primarily because calculus was invented simultaneously by two different people living in different parts of the world. Each one having no idea that there was somebody somewhere else in the world working on exactly the same thing. And so each person creates their own formulation, their own set of symbols for derivatives and so forth. If you're inventing this science, you have to create your own notation. So this is pretty much the style of notation that Isaac Newton created. This is the style of notation that Gottfried Leibniz created. And they both continue to exist down to this day. And this is one of those cases where it's not necessarily a bad thing that there are two different types of notation. In fact, maybe it's a good thing. There are advantages and disadvantage. D-I-S-A-D-V-A-N-T-A-G-E. Okay, I got it. There are advantages and disadvantages to both styles of notation. And maybe that's one of the reasons that both styles of notation are common down to this day. So we're going to reformulate the chain rule using the Leibniz style of notation. Okay, here we go, the Leibniz form of the chain rule. And we suppose that y is a function of the variable t, and that t is a function of the variable x. So y equals f of t for some function f, and t equals some function g of x for some function g. Here's the chain rule as we know it. The derivative with respect to x of f evaluated at g of x. It's the derivative of the outer evaluated at the inner times the derivative of the inner. So this is the chain rule as we know it. We'll call this Newton's form. Well, g of x is the same as t, right? So I can replace g of x here with the variable t. Now let's see, how do I replace this? This is the derivative of g as a function of x. And g of x and t are the same thing. So the derivative of g as a function of x would be exactly the same thing as the derivative of t as a function of x. And I'll write it this way. The derivative of t as a function of x. There. So these are equivalent. Now, what else can I do? Let's see. F of t, well, that's just y, isn't it? So I can continue this. F of t is y. And now, what do I do about this thing? This is the derivative of f as a function of t. But f as a function of t is the same as y. So the derivative of f as a function of t is the same as the derivative of y as a function of t. And I'll write it this way. The derivative of y as a function of t. And this thing, I like this just the way it is. So I won't change it one bit. Derivative of t as a function of x. And these two things are exactly the same. Now there's just one more thing that I need to do to get this in exactly the form that I want it. I'm computing the derivative of y with respect to x. So this is exactly the same thing as derivative of y as a function of x. So this whole thing, derivative of y as a function of x, and these two things, I like these just the way they are, so I am not going to change them. dy dt times dt dx. And this is the form that I was after. So that's the chain rule, the Leibniz form. And as I said earlier, there are advantages and disadvantages to each. This form, this is Isaac Newton's form. It's great for computation. If we're doing computation, this is the form that we want to use. It's not so good for explaining theoretical results. but it's great for computation. This form of the chain rule, the Leibniz form, not too good for computation. It's somewhat cumbersome, but it is great for explaining theoretical results in a way that make things easy to understand, things that would not be easy to understand otherwise. So primarily for computation, we're going to use the form that we've been using. We want to learn this form, though, because when we get to multivariable calculus, all of a sudden they're going to be using this form to explain results. And they're not going to introduce us to this form. They're just going to assume that we've been using this day and night for months and months and months, and we are really, really, really familiar with this form, which is not going to be the truth. So what we want to do now is become adept using this form so that as we get into the end of Cal 2 and the beginning of Cal 3, when our authors start using this form of the chain rule to explain some theoretical results, it won't be a complete shock to us. We'll understand this form of the chain rule and we'll know what's going on. Just for the sake of those who are studying and taking notes, and hopefully that's all of you, I'm writing the results down separately. The chain rule that we have been using, Newton's form, that's derivative of the outer, evaluated at the inner, times derivative of the inner. The Leibniz form, that we're assuming that y is a function of t and t is a function of x. So dy dx equals dy dt times dt dx. And again, notice the set of circumstances here. Y is a function of t and t is a function of x. So as we have the facts given to us here, y is not directly given as a function of x, but y is a function of t, and in turn t is a function of x. So at least indirectly y is a function of x, and because of that it makes sense to compute the derivative of y as a function of x. And when we do, this is the form of the chain rule that we use. Now, there is a memory aid that we want to use, and I'll write that down. And the memory aid is this. If we imagine each of these derivatives to be actual quotients or fractions, if we imagine these things to be quotients or fractions, then we can cancel out a common factor in numerator and denominator and get exactly the same expression on both sides. And here's what I'm talking about. Dy dx equals dy dt times dt dx. Now, if we imagine these things to be actual fractions, then we can cancel out the common factor, and we have the same expression on both sides, dy dx, dy dx. That's our memory aid to help us make sure that we've actually written the Leibniz form of the chain rule correctly. So after we write out the form of the chain rule that we're going to use in Leibniz form, we can do this mentally and just make sure we've written it correctly. We'll ask ourselves, okay, if I cancel out the dt's, do I have the same thing on the right side that I have on the left side? Let me see. If I cancel out the dt's, I have dy dx, dy dx. Yep, I've written it correctly. So that's a good memory aid for us to have, just to make sure that we write the Leibniz chain rule in the proper form. And why can't we just remember dy dx equals dy dt times dt dx? Because we're not always going to be dealing with the variables y, x, and t. Suppose we have u, v, and w instead. Well, dy dx equals dy dt times dt dx is not going to help too much in that situation. So what we want to do is just learn this canceling trick. Just imagine that we're canceling a common factor, and that gives us the same thing on both sides. Now let's do a few examples. Here's a nice one to warm up on. Genuinely a nice one to warm up on. We have y given as a function of t, and we have t given as a function of x. So at least indirectly, y is a function of x. And so it makes perfect sense for us to compute the derivative of y as a function of x. And they want us to do that using the Leibniz form of the chain rule. So what I'm going to do, and this is something I do sometimes in problem solving, just so that I make sure I have all of my weapons readily available before I launch the attack. I write down what it is that I know before I actually try to solve the problem. And this is one of those times that I do that. So I'm going to write down what I know. And actually, this is a little bit of a lie, because what I'm going to put down here are not things that we know, but they're things that we can easily deduce from the information that's given. So we don't know these things yet, but these are things that we can easily deduce from the information that they give us. Here they tell us that y is a function of t, and here's how y is defined. 3t squared plus 6t plus 2. So I'm bending the truth a little bit by saying that I know what dy dt is. I don't know what this thing is, but I can easily deduce what it is from the information that they give us. So let's see, how do I get dy dt? Well, I just compute the derivative of both sides of this equation as a function of t. If I compute the derivative of y as a function of t, I get dy dt. And if I compute the derivative of this side with respect to t, I get 6t plus 6. Like I said, this was not something that I knew, but it was something that I could easily deduce from the information that's given. Now, I can also deduce something else from the information that's given. I have t given as a sine of x. So I ought to be able to compute the derivative dt dx. And how do I get dt dx from this equation? Now, I compute the derivative of both sides of the equation with respect to x. So if I compute the derivative of t as a function of x, I get dt dx. And if I compute the derivative of sine of x as a function of x, I get cosine of x, right? So these were not things that we knew, but they were things that we could easily deduce. And now that we've written them down, these are things that we know. So we do know these things now. And they tell us they want dy dx using the Leibniz form of the chain rule. So this is what we want, the derivative of y as a function of x. Do we have that over here, dy dt, dt dx? No, we don't have that. So let's make sure we don't forget what we're looking for. We want dy dx. So I'm going to write that down just to make sure that we stay focused. This is what we want. And by the Leibniz form of the chain rule, well, this is what I want, dy dx. And if there's any justice in this world at all, hopefully I can use one or both of these things. I'm hoping. So let's see, dy dt and dt dx. It sure would be nice if I could use those things, especially since I know what they are. Does this work? Well, here's where that memory aid helps. If I imagine both of these things to be fractions and I cancel out the common factors, what happens? I cancel out the dt's, so I get dy dx on the right, I have dy dx on the left. Perfect. I've written it correctly. So now all I have to do is fill in the blanks. I know what dy dt is. I know what dt dx is. Dy dt, 6t plus 6. Dt dx, cosine of x. Now, normally we'd stop now and say, we're done. But there's something that I don't like about the appearance of this expression. Remember what I set out to do. I set out to compute the derivative of y as a function of x. And here's my answer. And the way I have my answer written, I have it written as a function of both t and x. But I want the derivative of y solely as a function of x. So I'm not going to settle for this. Solely in terms of x. Why x? Because I started out with the goal of computing the derivative of y as a function of x. So I want this whole thing to be in terms of x. So I got to get rid of this t. And I can't just replace it with an x because t and x are not the same thing. But they are related. Right up here, this tells us how t and x are related. T is the same thing as sine of x. So down here where I see t, I'm going to substitute sine of x. And I like this form of the answer. I'm going to leave it exactly like that. But for the sake of being thorough, I'll put my answer in a little box here. 6 sine of x plus 6 times cosine of x There's my answer. Voila. Well, you know what? I think we ought to do at least one more, maybe two. Here's a good one. Y equals tangent of x, and x equals 4t to the fifth plus 6t cubed plus 5. So let's see, y is a function of x, and x is a function of t. So at least indirectly, y is a function of t. So it makes sense for us to be able to compute the derivative of y as a function of t. And we're going to do that using the Leibniz form of the chain rule. So first, we create a box, and in the box we write what we know. Well, we don't know it yet, but we will know it. What we can easily deduce, okay, now I'm telling the whole truth. We can easily deduce the derivative of y as a function of x. Y is given to us directly as a function of x, so we should be able to compute the derivative of y as a function of x. And here's how we do it. We just compute the derivative of both sides of this equation as a function of x. The derivative of y as a function of x is dy dx. The derivative of tangent x as a function of x is, what's the derivative of tangent x as a function of x? It's one of those trig derivatives we should know. Secant squared x, there we go. Secant squared x. Now, since x is a function of t, we can also easily deduce the derivative of x as a function of t. And the way we do that is we look at this equation and we compute the derivative of both sides of this equation as a function of t. The derivative of this side of the equation as a function of t is dx dt. The derivative of x as a function of t is dx dt. The derivative of this side of the equation as a function of t, 20t to the fourth plus 18t squared. Yep, I guess that's it. So this is what we were able to deduce easily. This is what we know. What we want is the derivative of y as a function of t. Now, let's see. Do we have that over here? dy dt? No. dx dt? No. Okay. So we don't have dy dt yet, but that's what we want. We want dy dt. And I'm just writing this here so I won't forget what it was I was trying to do. And they want us to use the Leibniz form of the chain rule. Okay, so I'll put that down. The Leibniz form of the chain rule. We want dy dt. Now, it will be very helpful, it will be extremely helpful if we can use these things. Hopefully we can. Dy dx times dx dt. Hopefully this will work. Let's check. Remember the memory aid? If we view these things as fractions and mentally cancel out the common factor, we should get the same expression on both sides of the equation. So mentally we cancel out the dx's, and we get dy dt on the right, dy dt on the left. Bingo, we got it. This is the correct form of the Leibniz chain rule. This is the form we want. So let's just take the expression for each of these derivatives and plug them in. Dy dx, that's secant squared x. And dx dt, that's 20t to the fourth plus 18t squared. And, you know, the same thing that happened last time happens this time too. My derivative is given in two different variables. My goal was to compute the derivative of y as a function of t. And what do I have? I have the derivative of y in terms of x and t. That's not going to do. So I'll say re-express solely in terms of this variable. Now, why that variable? I want the derivative of y as a function of t. So I want all of this mess to be stated in terms of t. So I've got to get rid of the x. So I'm going to rewrite it here. Secant squared x, that's the bad guy right there. I have to replace x with an equivalent expression in terms of t, and this tells me how to do it. This gives me x in terms of t. So instead of putting x here, I'll put this expression in terms of t. 4t to the fifth plus 6t cubed plus 5. Okay. I got rid of my x and exchanged it for t's. And this factor, there was nothing wrong with this in the first place, was there? So I'll just write it down again. 20t to the fourth plus 18t squared. And that is exactly what I want. Bravo, bravo. Now I guess just one more. And I want to do one more. I want to have an example that doesn't have x's, it doesn't have y's, it doesn't have t's, just so that we'll have to really understand how to write the Leibniz form of the chain rule correctly in terms of whatever variables we have. One last Leibniz chain rule example. Theta equals w to the fifth minus 6w cubed plus 4, and w equals secant of alpha. Now, theta is not directly given as a function of alpha, but theta is a function of w, and in turn, w is a function of alpha. So it makes sense to be able to compute the derivative of theta with respect to alpha, because at least indirectly, theta is a function of alpha. So we're asked to compute the derivative of theta with respect to alpha using the Leibniz form of the chain rule. And before we go any further, let me just do something. Even after I became a good student, I didn't really know what a lot of the Greek letters were. And I'd see them in the mathematical literature, and I'd just see, okay, thing equals w to the fifth minus 6w cubed plus 4. W equals secant of thing. And I didn't know the names of the variables, but I didn't really think I needed to know. But I found out that learning the names of the Greek letters that are commonly used in math and science is very helpful. It's very helpful to be able to look at this thing and call it theta. It's very helpful to be able to look at this thing and know that it's alpha. And so that's what I'm going to do right now. These things, if we don't know what they are, this is the Greek letter theta. And this guy right here, this is alpha. And I just want to write that down just so that we'll know. And if we have to use other Greek letters in our conversations, I'll write their names down. I'll write their names down too. There really is a benefit to be derived from knowing the names of these letters, instead of just doing what I used to do, which is say, thing is w fifth minus 6w cubed plus 4, and w is secant of thing. It was hard for me to really understand what it was I was working with because I didn't know the names of the Greek letters. So just to start us off, this guy is theta, this guy is alpha. Now, let's get on to our Leibniz chain rule exercise. We want to compute the derivative of theta as a function of alpha. And they are related, but indirectly. So let's write down what we know. Theta is a function of w, so we ought to be able to compute the derivative of theta as a function of w. We should be able to deduce what this is. And the way we do that, we look at the equation that relates the two variables. and we compute with respect to w the derivative of both sides. We compute the derivative of both sides as a function of w. The derivative of theta as a function of w is d theta dw. And the derivative of this expression with respect to w is 5w to the fourth minus 18w squared. So we have d theta dw. We got what we could from this equation. Now let's go over here and milk this equation for all it's worth. Since w is a function of alpha, we ought to be able to compute the derivative of w as a function of alpha. And here's how we do it. We compute the derivative of both sides of the equation as a function of alpha. The derivative of w as a function of alpha is just dw, d alpha. And the derivative of secant as a function of alpha is secant alpha times tangent alpha. So these are the things that we now know, things that we could easily deduce from the information given. Now, are either of these things exactly what we want? No, we want d theta d alpha. So we don't have what we want yet. So let's write down what it is that we want so that we don't forget what we're trying to do. We want d theta d alpha. And we have to use the Leibniz form of the chain rule to get it. So we want d alpha d theta. My foot, we do. We want d theta d alpha. And hopefully these two derivatives are exactly what we need. Let's see. D theta dw, dw d alpha. So I'll write d theta dw times dw d alpha. And before I go any further, let me make sure that I've written it correctly. If I've written it correctly, then I should be able to imagine these two derivatives as being quotients or fractions. And I should be able to imagine myself canceling out the common factor of dw. And if I imagine myself canceling out the dw's, I should have the same thing on both sides. I should have d theta d alpha, d theta d alpha. Okay, it works. If I imagine myself canceling out the dw's, I have d theta d alpha on the right, d theta d alpha on the left. It means I've written it correctly. So, full steam ahead. D theta dw, that's 5w to the fourth minus 18w squared. And dw d alpha, that's secant alpha times tangent alpha. And again, there's something not quite acceptable about the form that we have our answer in. we want to compute the derivative of theta as a function of alpha, but we have the derivative of theta in terms of both W and alpha. No good. So, rewrite solely in terms of alpha. Why alpha? Because we want the derivative of theta as a function of alpha. Which means the W's got to go. We have to replace the W's with their equivalent in terms of alpha. And here's the relation that shows us how to do that. This tells us that W and secant of alpha are exactly one and the same thing. So, d theta d alpha is equal to 5, okay, W to the fourth, that's what's unacceptable. I got to replace the W with secant alpha. So 5 W to the fourth, or secant alpha to the fourth, minus 18 W, can't have a W, so we replace the W with secant alpha. W squared or secant alpha squared and then times secant alpha tangent alpha. And I like that form just fine. So I will encapsulate it, and I will leave that as my final answer. Congratulations, we have learned the Leibniz form of the chain rule. We're going to do some homework to get it down pat. And those of us who are going on to Cal 2 and Cal 3, when our authors start talking about functions of 2 or more variables and they use the Leibniz form of the chain rule to derive their results, we will look at that and we will know exactly what's going on. So this concludes everything that we've done with the chain rule. This is our last chain rule lecture. I will be giving you some homework shortly, but we are done with the chain rule as of right now. All we have to do is the homework exercises for the chain rule, which I will send out shortly.